Hey, what's up guys? So in this video, we're going to discuss the last type of forces that is relevant for this chapter, basically upthrust. At the same time, we're going to introduce relevant concepts such as the pressure, the Archimedes principle, as well as the principle of flotation. So this is the last type of forces that is going to be discussed for this chapter. Okay, it must of course ends with a bang. So as you can see here, learning objective, we have a total of 6 objectives to go through just for this lecture. So obviously it's going to be content heavy. At the same time, upthrust is something that is really new to you, okay, not introduced in O level, but totally new for A level. So yep, so please pay attention. So pressure. Pressure is the force per unit area acting on the object. So P is equals to F over A, that's the formula. P being the pressure, force being the normal force. So it has to be the perpendicular force that is acting across the cross-sectional area over which the force acts. So A being the cross-sectional area. So in the diagrammatic view, this is how it looks like. So do take note that the force needs to be the one that is perpendicular. So in the case whereby there is a certain force that is not perpendicular to the surface, only the component that is perpendicular to the surface will be contributing to the pressure. So pressure is also a scalar. The SI unit is Pascal. So moving on, pressure in the liquid, something that you have learned in O level before, but now you probably need to derive it, so learn the derivation well as well. So consider a volume of liquid of height h, cross-sectional area A, and density rho. So we have the volume of the liquid being the volume of the cylinder, cross-sectional area times height. The mass of the liquid volume is volume times density. How do we get that? Basically mass over volume is density. So all I need to do is to make mass the subject. So mass will be equals to volume times density, thereby giving us this formula written on the slide. So volume times density. Volume, we know that it is actually cross-sectional area times height. So substitute into the equation, we get AH rho. So the weight of the liquid column is basically m times g. So therefore AH rho g. So why do we even want to derive the weight itself? Because weight is a force across the cross-section area. The weight of the liquid column must be contributing to some pressure. But do take note at the same time, there is also atmospheric pressure acting on the surface of the liquid. So therefore, this together with the weight of the liquid, okay, both of them will have a total pressure acting on the base of the liquid column. So therefore, the pressure at the base of the liquid column is basically the pressure at the surface plus the pressure due to the weight itself. So pressure of the atmospheric pressure plus the normal force over area, the normal force being the weight of the liquid column. So weight is AH rho g as derived previously. So PATM plus AH rho g over A give me the total pressure at the base of the liquid column. So take note that I can actually cancel the A away. So it simplified to become atmospheric pressure plus H rho g. So H rho g should be something that you're familiar. And basically we have already derived, okay, the formula that we really need, just another few more steps. So the pressure difference due to the liquid column only itself, okay, is basically PATM plus H rho g minus PATM. So giving us H rho g. So H rho g is just the pressure provided by the liquid column. Okay, so some food for thoughts. Okay, are the pressure in point A and B below the same? So basically, the way you should think about it is the water column heights, both of them are h. So therefore, using the formula P equals to H rho g, you should be able to come out to the conclusion that both A and B, same height, same rho, same g, they should therefore contribute to the same pressure. Also, at the same time, the atmospheric pressure above both water columns should also logically assume to be the same. So therefore, the answer is actually yes. Okay, the pressure at point A and point B below are the same. But some of you may be thinking that this is a slanted water column, so therefore the volume should therefore be larger, and logically, therefore, the mass should be larger. The weight, okay, of the water column above point A should also be larger. So therefore, why not the pressure being larger? So that is true. Okay, I do agree with you, but at the same time, do notice that not the full weight is exerted on the surface area of A. Part of the weight is actually supported by the wall of the water of the test tube itself. So therefore, I guess it kind of work out. So here, having a smaller volume, but the full weight is exerted on the surface, the water surface at point B. But for the other part of the diagram for point A, even though there is a larger volume, larger weight, not the full weight is actually exerted on the surface of A. Part of it is exerted on the surface of the wall. So I guess it kind of work out. So therefore, the pressure logically can be the same. So here you can see that there is water shooting out from a lower point of the container, and from that point, the water shot further away from one that is at a higher point. And this should be obvious because the water pressure at the lower point is higher, and that forced the water to be able to shoot further away. But look at what happens when the little boy dropped the water container. You see that when he dropped the container, the water no longer shoots out. Okay, that is going to be a slow-mo. You can see that when he drops the water, okay, when he drops the water cup, you can see that there is no water being shot out from the water cup anymore. And guess what's the reason why? Okay, so once again, recall just now what I mentioned. How come this part it actually shoots further away? Because the pressure is higher. And what essentially builds up the pressure? Pressure is there because there is a stationary base, and therefore the water molecules from the top is pressing down on the water molecules below. That gives rise to pressure. But when it is actually dropped, okay, when the thing is dropped, all the water molecules is actually on free fall. So if they are all free falling, you can understand that therefore the water molecules is actually not pressing on each other, and therefore there should no longer be pressure difference in the water column, or in this case in the water cup. And because there's no more pressure difference, the water will not shoot out from the hole of the water cup anymore. So that's the idea you need to understand from this particular example, and it will be related to upthrust later. Okay. So now let's do an example. So in this example, we need to understand how does the pressure changes, okay, from above the surface of the container. So something that you should take note here is liquid M is at the bottom must be because it has a larger density. And therefore, it is also stated in the question, the density is actually twice as great as that of the liquid L. So therefore, the answer should logically be C and not A. Why? From the equation P is equal to H rho G, rho and G is basically the gradient, okay, of the equation. So the higher the density, the higher, the larger the gradient, okay? And the pressure at the bottom should therefore be the largest since there is both air as well as the liquid pressure acting on the bottom of the container. So therefore, it should always start at the highest point. And like I mentioned just now, liquid M has a higher density, so therefore when the point move up, okay, it should have a larger gradient drop. And then when it moves towards L, it should have a lower gradient drop. And finally, when it exits the surface of the liquid, there are still atmospheric pressure. The pressure cannot be zero. Okay, so therefore there is a somewhat, okay, very gentle, close to constant, okay, change of pressure above the liquid surface. And therefore, answer should logically be C. So the solution here is not written in your lecture note. So pause the video and then copy the the qualitative explanation to your lecture notes. Okay, so let me move on. So now I have another video, okay, describing to you how does pressure really looks like in the balloon. Okay, so this little boy is going to poke the water balloon, and then the water balloon is going to burst, and then look at how the water actually fly in this case. You can see that, okay, when he bursts the balloon, the water is actually being thrown in all direction. Okay, so what does that tells me? It tells me that the pressure in the balloon is actually all directional. Okay, it is not only acting downward. The water molecules here seems to be shooting perpendicular away from the surface of the balloon. Here shooting like that, here shooting away here shooting away here, whereas those at the bottom seem to be shooting diagonally downwards. Okay, so the whole idea of this video is to show to you that the pressure, okay, in the water is not only downward. There are also pressure upward, okay, and the understanding of this is kind of useful to understand upthrust. So finally, upthrust. Upthrust is basically an outward force exerted by fluids, and it arises due to a difference in pressure. You may not fully appreciate the explanation here, but let me continue first and I'll explain in a while. So basically consider lifting an object under water versus lifting it in air. The difference between water and air in this case is of course water is being more dense, okay? And you will understand later when the formula is being introduced that this characteristic of being more dense will actually contribute to a larger upthrust. So the object in the water seems less heavy. So some everyday experience as well. When you're swimming, you probably will also feel that you are lighter, okay, in the water versus when you're standing on concrete ground in air. So the effect here is because there's a buoyancy force or upthrust acting upward on you. So this will result, okay, in T2 being less than T1, T2 being less than T1, okay. So the upthrust once again is really due to the difference in pressure acting on the upper and lower surface of the object when it is in the fluid. So basically think about this. The surface here, okay, is in the shallower part of the water. The surface here or the bottom here is definitely in the deeper part of the water. And based on pressure being H rho G, the larger the H, the larger the pressure. So definitely the pressure at the bottom surface is going to be greater than those at the top. So there must be a difference in pressure, and this difference in pressure must be given by the delta H times rho times G. Rho being the density of the water, G being the gravitation acceleration, and delta H is really the difference in height. Okay, this will be delta H. So essentially, when there's a difference in pressure and pressure is equals to force over area, there must also be a difference in force. So the difference in force is essentially the upward force provided by the upthrust. At the same time, okay, you must understand that the water pressure based on the balloon example just now, okay, the water pressure is in all direction. So there are also forces acting horizontally against the side of the object, but they will cancel out each other because the pressure at the same level basically must be the same. So at the sides, they will all cancel out each other. Finally, you see here there's this water displaced by the object. The water displaced by the object is essentially, okay, the upthrust. The weight of the water displaced by the object is essentially upthrust. So just imagine before I sunk the object into the water and it was filled to the brim as well. So basically now I put the object in. So this volume taken out by the object was originally taken out by the water. Okay, so this water, okay, this volume of water is basically the volume displaced by the object. And this volume multiplied by the density times G, basically that gives you the weight of the water displaced. And without explaining further first, you should understand that this is actually the magnitude of the upthrust exerted on the object. So now, upthrust once again is the outward force exerted by the fluid on the submerged or floating object, and it arises because of the difference in pressure. So fluid can be gas or liquid, okay? But because in air, air's density is normally small, and based on what I described just now, density contributes to upthrust. So therefore, normally it is insignificant because the density of air is normally much smaller than the density of any object, okay, placed in air. So once again, also upthrust is not air resistance. Air resistance is a viscous force and it exists only when the object is moving through air. But upthrust is also present, okay, even if the object is not moving, because as long as there's a difference in pressure, there must be an upthrust. So let's take for this example, I have a balloon, okay, the balloon there's also air inside. So both the balloon and the air inside must have weight. So weight is downward pointing. At the same time, we can see that the rubber band looks stretched, so there must be a tension. And tension is a pulling force, so it must be pulling the balloon down. So you can see that there are two forces acting downward, yet the balloon seems to be floating. And what's the reason? The reason must be because there is an upward force to keep it in equilibrium, and this upward force is essentially the upthrust. So to derive the formula for upthrust, upthrust is essentially the difference between two pressure force. And what exactly are pressure force? We know that pressure is equal to force over area. So basically for a pressure exerted across an area, the force is simply given by P times A. So F1 and F2 arises simply because there is a pressure 2 exerted at the bottom and there is also a pressure 1 exerted at the top. So essentially pressure is also given by H rho G. So P1 is essentially given by H1 rho G and P2 given by H2 rho G. Taking note that rho is actually the density of the fluid. So therefore we have this formula here. Factorizing the common factor out, what do we get? We get, okay, this expression here, and H2 and H1 is essentially the length of the object, the height of the object. So with that L multiplied by A, that gives us the volume of the object. So therefore, we derive the formula for upthrust as V rho G. Okay, something that you need to remember before you blindly apply the formula. Rho F is essentially the density of the fluid. Okay, it is not the density of the of the object. It should be the density of the fluid. So take note, what do you substitute in here whenever you apply the formula for upthrust. At the same time, V, even though here we say that V is actually the volume of the object, what I want to clarify here is volume of the object submerged. Okay, V should have been the volume of the object submerged. So there are cases whereby the object is floating and maybe not the full volume of the object being submerged into the water or into the fluid, how we use the formula here is we are only considering the portion of the object that is submerged within the liquid. And that being said, one last thing that you need to remember here is the volume of the object submerged is simply replacing the volume of the fluid that was originally there. So it is the same thing to say that the volume of the object submerged is also equals to the volume of the fluid displaced. So by looking at this, okay, let us now move on to Archimedes' principle. So what Archimedes' principle is trying to define here is essentially the formula for upthrust. So here it says that upthrust is equals to the magnitude and opposite in direction to the weight of the fluid displaced by the submerged or floating object. So how come it is the weight of the fluid displaced? Now let us look at the formula in detail again. So rho f is the density of the fluid, not the object. V is the volume of the object submerged, just like what I mentioned just now. And this is equivalent to the volume of the fluid displaced as mentioned previously also. So V rho Fg is essentially the weight of the fluid that has been displaced by the object. And how do I see that? Since rho F is equals to density of the fluid, and that should be given by mass of the fluid over the volume of the fluid displaced, and since we know V is the volume of the object submerged is also equal to the volume of the fluid displaced, so V and rho F is essentially the mass of the fluid, and that mass of the fluid multiplied by G, that gives us the weight of the fluid displaced. Okay, I should have added in the word displaced here. So V rho G, in this case, where we calculate upthrust, we are essentially calculating the weight of the fluid displaced. So in this picture that we have seen just now, if I actually want to find out the magnitude of the upthrust, essentially I'm just trying to measure the weight of this fluid displaced here. So finally, we move on to the last principle, the principle of flotation. But to discuss the principle of flotation, I would like to compare it with Archimedes' principle. So as mentioned just now, Archimedes' principle simply tells us that the magnitude of the upthrust must always be equal to the weight of the fluid displaced. So basically V rho G. But what principle of flotation is telling us is only under the condition that an object floats, then the upthrust acting on it must be equal to the weight of the object. Okay, so the upward force must be equal to the downward force, so upthrust equals to the weight of the object. So just to clarify a little bit more between the two principles, what Archimedes' principle is telling me is, okay, upthrust is always equals to the weight of the fluid displaced. Regardless whether an object is floating or not, it is always equals to the weight of the fluid displaced. But for the principle of flotation, first and foremost, the condition here is it must float, and only when it floats, then the weight of the object is also numerically equals to the weight of the fluid displaced. Okay, so essentially, Archimedes' principle is still defining this part of the equation, but for the principle of flotation to happen, when the object floats, the upward force upthrust must also be equal to the weight of the object. So here we have two examples. So in the first example here, we have an object that is completely submerged but suspended. So basically suspended tells me that the object is actually floating. So if it's floating, then the upthrust is equals to the weight of the object. And upthrust is given by weight of the fluid displaced, which is basically V rho G, volume submerged, multiplied by the density of the fluid multiplied by G. But weight of the object is essentially the volume of the object multiplied by the density of the object multiplied by G. And since in this case it is completely submerged, the volume submerged is also equals to the volume of the object, and that's why they share the common notation, and I can actually cancel them off, leaving me with density of the fluid equals to density of the object. In the second example here, we have an object that is partially submerged. Okay, partially submerged means only a portion V2 is submerged under water, whereas there's a portion V1 that is above the fluid. So upthrust equals to weight of the object. Because it is floating, upthrust must be equal to weight of the object. And upthrust, as defined by Archimedes' principle, it is still equals to the weight of the fluid displaced. So therefore, in this case, upthrust is given by V2, only the volume of the object submerged, multiplied by density of the fluid, multiplied by G. But for the weight of the object, I need to consider the whole object volume, which is V1 plus V2, multiplied by the density of the object. And therefore, from this here, we can therefore derive the volume of the object must be lower than, the density of the object must be lower than the density of the fluid. Okay, as this Upthrust lecture is getting a little bit lengthy, I've decided to split it into a two-part series. So for the first part, I've already completed all the content for Upthrust. In the second part, I'll be going through all the work example 9 to 13, as well as some other additional examples and videos to consolidate your understanding a little bit further. So if your tutor is going to go through the work example 9 to 13 with you during the live lesson later, you may skip the part 2 and go straight to the next section, center of gravity and movements of a force. Otherwise, if you're interested, you can also watch the later portion of the part 2 to listen to the additional example that I'll be going through beyond the lecture notes. Okay, thanks, bye!